Professor Enrico uh, for this very informative and interesting workshop, and hope you will enjoy his talk. The floor is now with Professor Enrico. Thank you very much for joining us.
Thank you very much, Professor Zaidi, and thank you very much to the organizer to invite me to participate to this workshop. I would like to be in Doha as soon as possible in presence, but for the moment, is also I'm very interested to start to discuss with you on what is going on in the field of your also interest related to the desalination problem and to the new potentiality of membrane desalination. So when you read the title, you see I'm not talking about just water. I'm talking about membrane operation for minerals recovery. Everybody is familiar with the problem with the water stress problem. Just a moment. Come facciamo andare avanti? Anybody is very familiar with the water stress problem all around the world. In your area, in the Middle East, particularly, you are living through desalination until now. Today, you have to consider desalination will be much, much more in the future than just a system to produce fresh water. Fresh water is very important, but something more is becoming important today. And desalination, particularly when related to membrane operation, can be the way to face not only the water stress, the water shortage that is present today all around the world, in the Middle East particularly, and will be present for the next decades all around the world and becoming more and more severe in some cases. But what is becoming more severe is the raw materials depletion. And the large public is much less informed on this problem. Today, also in Europe, in Italy, if you want to buy a car, we have a long delay. You have to wait months, in some case 1 or 2 years before having your car available, because the material necessary for producing this sophisticated part of your the car, the electronic part, all the chips and similar are no more available, because the raw material depletion has been affected in the last 100 years, most part of the world, having disappearing between, you see, 70% to 85% of a lot of minerals, very important and strategic. Now, all around the world, we are starting to be aware, and something has to be done very, very quickly, otherwise the situation will be complicated. Just some example here of some minerals that are disappearing largely, and in the meantime the demand is growing and growing in here. The case typically is lithium, and the case is uranium. And both these minerals are strategic. Now, what is interesting that in principle the conclusion of our discussion will be that desalination in the future will not be just a system to produce fresh water. It will be a system to produce also fresh water, but the main interest, the main significant contribution to the industrial development will be for the minerals recovery and energy production, what we call blue energy related to the salinity gradients. Maybe later on in the day there is another presentation that will emphasize this aspect. I will not touch it. So that is the problem I will emphasize, is the problem of desalination, not looking only to the fresh water in the permate, but looking mainly what is happening on the feed side, on the brine. And the brine is no more a problem. The brine disposal problem is not really the way of approaching the situation. Brine is the real value of the desalination more and more. And this is a typical example. Now, if you look at what is in the ocean, you will see that the ocean is a liquid polymetallic ore. That means the traditional mines in the future, if appropriate technology will be available, will compete with the traditional mines on Earth, There will be no more excavation underground, etc., but a lot of the minerals necessary can be in principle found down in during desalination on the feed side and not in the permeate. Something already is doing around on magnesium, potassium, etc. There are part also in the Middle East and the area that where these things are going. But what is important today now for our discussion, that if you check what the concentration of the minerals on the land and how much minerals have been are producing normally in following the traditional way of doing, you will see that the concentration of these minerals in the brine of the existing membrane desalination unit, reverse osmosis units, is in some case similar. If you look on this number for magnesium, just if you extract the magnesium from the brine of the existing RO plants running around the world, in Middle East or in Australia, etc., we can basically double, increasing 100% this magnesium production on Earth per year, just by recovering the mineral that we are not recovering today, and we just send back in the sea or underground, etc., losing money. Lithium, same story. 30% of lithium can be just extracted from the brine of the existing plant. Calculation from this table, we were assuming recovery factor very conservative, 45%. Rejection of this our membrane 99.6, which is the average value for most part of the system. So you can see here the concentration in brine of iron, uranium, arsenic, vanadium, aluminum, and this is quite interesting. So if we have appropriate technology to treat in the right way the brine of our plant, this kind of new strategy can be realized. This is based on not on osmotic phenomena, because osmotic phenomena, reverse osmosis, as you know, by the thermodynamics, cannot concentrate more than a certain value. You have to go to very, very high pressure on the feed side, which is making the system practically not realistic. If you go in, going to use membrane operation very different, what we call membrane contactors, which are hydrophobic materials, microporous membranes, so very different than the traditional dense skin polyamide membranes that we are using in RO. You can realize this kind of situation where in membrane distillation, transmembrane flux is practically independent from the feed concentration, just the opposite what happened in reverse osmosis. So the flux is still constant across the membranes, or there is relatively low decay when you have a very high concentration of your salt on the feed side, the brine. And if you just now are able to have good chemical engineers who can still hand control the situation, and you can introduce a cooler crystallization units in the system where the crystal that you are forming can be continuously removed, you can combine freshwater production downstream your membranes with a continuous crystal formation and extraction of different elements from the sea. Quite interesting units, and it works, and it's becoming more and more of interest worldwide. There is a project in Europe. There are 3, 4, 5 huge multinational projects sponsored by the European Union in progress, based on the logic of extracting minerals from the brines. And so that is the concept, and the membrane engineering. Still a lot of work has to be done, but the work done has been excellent. Here at ITM, we are working from many years already in this area, and more we are interested and enthusiastic in the opportunities that can be realized for solving not only the water stress, but also the minerals depletion problems and energy production, and using the blue energy concept. So energy, water, and minerals can be the final output from desalination. So the country as Middle East where desalination is important will be very, very lucky if they will insist and develop this technology. Research has still to do a lot of work. Keep in mind that one part important that people have to learn, not only you are producing crystals, but if you are smart, you can produce crystals with very specific properties and quality. You can produce just a specific polymorph. If you have to produce, for example, and you want to extract magnesium sulfate, you don't produce magnesium sulfate. You know how to produce epsomite. Epsomite is one of the possible final polymorph of the magnesium sulfate with 7 molecules of water and has a certain higher value than the traditional magnesium sulfate with less water and or no water at all. And that can be done because the assisted membrane crystallizers, that means membrane distillation working in a membrane crystallization mode, are able to realize a very well-controlled nucleation and heterogeneous crystallization. So the heterogeneous crystallization can be controlled by the uniform distribution of the pore, the very large uniform size of the most part of the pore in your membrane. A better membrane can be realized on this line, which you cannot realize in any traditional crystallization mode. So quite interesting and important. That is the case you can find already in the literature, where we are separating magnesium sulfate at 25 degrees as just epsomite. We separate the calcium that precipitate earlier just by chemical precipitation. And you can see uniform distribution of epsomite crystals with a variance, that means the quality of the crystals much, much better and higher than the one you can realize in any form of traditional crystallization normally. Normally the CV, that means the variance is of the order of 50, 60, 65 in general. Here you can go down to 33 to 32. That means a very narrow, sharp distribution of the geometric properties of the minerals that you are producing. More than this, if you make a very draft preliminary calculation, you can see here, in this case, you don't measure the cost of the water, but you measure the annual profit. You say in the first table on the last column on the right, and in this plant with this kind of integration, membrane filtration, nanofiltration pretreatment, reverse osmosis, and on the concentrate, ORO, and also nanofiltration, you can introduce membrane crystallized and membrane distillation. At the end, you have don't pay for the water. You have money coming in for selling the profit of the salt you are producing. $6 million, about $400,000 for this kind of configuration with the number that we have been using. And also in this case, you can check the number. This number will change many times, but you can check this number in the literature and you will see the logic that we have had. Keep in mind that important was mentioning coefficient of variation, CV, between 50 and 30%. Very interesting, very significant, reproducible. You have very difficult to have the same numbers with traditional evaporation methods to concentrate your salt, etc., etc. And this is the quality of the crystal. So that can be an interesting approach. We are talking about magnesium, but that the same can be done for any other thing, including lithium, uranium, rubidium, cesium, vanadium, barium, etc. Here is a summary for a cubic meter of in nano F. You can see that you can have about this 52 kilo of salts of this of magnesium 1010, sodium chloride 42, etc., etc. Not so easy, however, to extrapolate. If you go, you have to learn a lot, and still every day we are learning. A lot of work has still to be done. If you want to see what's so nice, why don't we try to extract lithium and solving the problem of lithium battery that is becoming very severe? Try to do it, does not work. Does not work. You can see here the transmembrane flux. If you're using what we call a direct contact membrane distillation for clean solution of lithium chloride, transmembrane flux will not be independent from the feed concentration, but with time and increasing the feed concentration, the flux is going down, and it will arrive zero transmembrane flux, approaching already 7 molar per liter, so the concentration of 7 molar. Crystallization of lithium chloride will take place only at 14 molar, not 7. So no crystal can be, you can still produce concentrate solution, but no crystallization. And we want to have crystal because that's the way to reduce the cost of the water you are producing and making eventually profit. But if you know how to do it and you insist to spend time, you can see now here the system works. You can change your membrane distillation design and configuration, not using direct contact membrane distillation, but using vacuum membrane distillation, and you can see here that you can approach 14 molar still with a nice transmembrane flux, and you can produce a nice lithium chloride crystal. These are the one that we are producing. You can see already here 2 different configuration, final habits, some linear one, some cubic, and that is a function of the material, and we are learning function of the material, function of the temperature. So that's the point. We have to learn. And if you do this experiment, be careful. We are learning that normally you're assuming that the chemistry of the material in microporous hydrophobic membranes is not very affecting the operation. In reverse osmosis, the chemistry of the material is very important, not in microfiltration or in contactors, not at all. In this case, you can learn, if you are doing these experiments with PVDF, eventually with coating of Iflon, no, it's impossible, no crystal. We have a very easy wetting of your membrane, so you are losing the hydrophobic properties and no crystal will be formed. If you want to have a crystal, you have to use different material. For example, as you can see here, when you are working with polypropylene, no wetting, and crystal can be formed. When you are working with ceramic membranes, the CMS, etc., no wetting, a crystal can be formed. So there is a significant study to be carried on, where you have to understand which kind of material can help you in always working in hydrophobic microporous membrane at a very high concentration in crystallization mode to operate and to solve your problem. This is something still going. You can just summarize something. Now we publish only data on lithium, but you can observe similar phenomena, very significant, with other interesting minerals. Rubidium, for example, some rare earths, some other salts, bivalent, monovalent, etc. So something has to be understood. We know now that, first of all, don't work with direct contact membrane distillation. Vacuum membrane distillation can solve your problem and not direct contact. And that's because you can realize the highest pressure driving force, but there is also a better control in temperature polarization phenomena because you don't have cold concentration profile on the permeate side of your membrane, etc., etc. And that is the situation, by the way, also trying to understand, and that's something that has to be done more and more in detail, the origin of the wetting. What is happening? Why is happening with lithium chloride and with and PVDF and not with ceramic and not with polypropylene? At the moment, you can suggest that the electronegative properties of fluorine atom, the fluorine is at the origin. When fluorine is not present, the system works. You can concentrate with no wetting. As soon as you have fluorine, coatings on some ceramic membranes, eventually, or coatings on the PVDF, as we were working, you have wetting. And that can be the chemical problem related to the interaction between the lithium ions and the fluorine. If there is no fluorine, so most part of the membranes we have been using until now in membrane distillation are not appropriate for this kind of operation. So that is very interesting open field to make more progress. These are interesting ceramic membranes that we are producing together with the colleagues from Taiwan. And you can see here very nice lithium chloride crystals that we can produce from continuously at changing also the final abyss, changing the temperature. This is a high temperature and low temp at 70 degree. If you go to 50, 40, you have totally different configuration. So there's a lot of to be done for understanding more what is happening on, and there is a effect related to the also working on the ceramic membrane as expected. You can see here there are some data between M1 and M4 ceramic in which this thickness of the membrane layer is just changing the transmembrane flux, different in expansion of temperature also. That is something expected, but that is telling you that if you are able to produce hydrophobic ceramic membranes, particularly with no fluorine, these kind of membranes that we have not been using too much on large-scale application in desalination or in crystallization until now, will have an interesting future. We are trying to produce more and more of this. You know, concentration polarization does not affect this operation. What is affecting, however, and chemical engineers have still to optimize and develop appropriate modeling and simulation of the system is the temperature polarization. Temperature polarization is much more complicated to control than concentration polarization, also because the two phenomenal polarization, temperature and concentration, are interrelated. And when we say that concentration polarization is not present, but concentration polarization can be affected by temperature polarization and vice versa. And until now, if you go in the open literature, not too much is present analyzing the situation. The other part of the story I told you, traditional material that people have been using, that we have been using and are using still today as PVDF, are not the one appropriate for if you want to develop more the strategy we are suggesting. More and more mineral extraction using membrane crystallizer. The system cannot work, can work for writing nice paper. We wrote many papers, but if you want to scale up and to go large scale with 1,000 square meter membranes, as we are using reverse osmosis, the kind of material we have been using until now are not appropriate. So we have to look more and more. Everybody is looking now to carbon nanotubes, to graphene and similar interesting properties in terms of anti-fouling properties, hydrophobic in nature, most of them. But, for example, graphene is very, very high thermal conductivity, and so that the concentration, the temperature polarization can be significant. However, this is material that makes sense still to study and to control the situation. But what is more interesting, and that's is the possibility to use these 2D materials, not just graphene, but these salts as bismuth telluride, these chalcogenides, all these kind of minerals and salt, totally unknown to me. I'm a professor in chemistry. I never heard before. I'm learning just now. This bismuth telluride, bismuth thin, or selenide, etc., etc. This material can be used as a filler of other material as PVDF or polypropylene or similar. Bismuth chalcogenides is something that we have been using. You can find in the literature, and you can have interesting flux with time as function of the temperature. You can change, and that can be quite interesting alternative to the traditional PVDF and similar. Particularly because in some case, you can see here, we are interested in crystallization. I show you in the table the real value, the cost, the profit of the process is not just the water you are producing. This you can go for free. You can distribute to the people who don't like to pay for the fresh water, by the way, and you can make your profit by the crystallization and selling of minerals with strategic importance: lithium, uranium, magnesium, rubidium, etc., etc. So how to crystallize well and fast? You can see here, for example, that if you compare the kinetic of crystal growth with this pristine PVDF, just membrane PVDF, the one people are using normally, with this PVDF fillet, with this bismuth selenide, the kinetic of crystal growth is increasing significantly. And that can be improved more and understood more, can be quite interesting. We are trying to give some suggestion in terms of the vacancy formed through the presence of these crystals on the surface, etc., etc. But in my feeling is that much more has to be understood, and hopefully young students will work on this and will try to handle better this kind of situation. This is again example of the possibility to produce quite interesting transmembrane flux and crystals in using these 2D materials as filler in some hydrophobic polymeric matrix. And all the results are showing you is clearly visible crystals of high quality, uniform form and distribution, much better in terms of variance than any other situation that we have been studying. So in principle, we can just work with this situation to try not only to compete and solving water stress, but also to solving this mineral depletion, which is affecting our daily life already now, and much more will be in the future. We are also starting to work on mixture of different salts, and that is one of the areas most important for the perspective. Not single salt solution will be of interest at industrial level. Here are some data on sodium chloride and sodium sulfate, and in some case we also have lithium already there, and we know that we can crystallize the sodium sulfate and having a recovery, in this case not very high, 40% sodium sulfite of good quality, specific with very good variance, etc., and in parallel to the production of sodium chloride. This work is just starting. There is a lot of work to be done, but this is the kind of area where more attention has to be paid. Here you can see also this, in this case, playing with the temperature using membrane-assisted crystallizer, you can also decide which kind of final crystal habit you want to produce. This for the sodium sulfate, you can see that at 30 degrees we have hexagonal thenardite present. That means sodium sulfate anhydrous, 100%. And in this kind of hexagonal configuration, if you go to 45, you are producing 100% this needle-shaped thenardite, very different, and in the same quality. So the we can also handle and separate in this way. Now, crystallization already from centuries is the best way to produce clean materials and to control the final habits. That means catalytic activity, some case optical activity, some case plasmonic activity is very important today, as shown. And this is not the most important in sodium sulfate, but that's what can be done. Changing from 30, going to 45, you can have two totally different forms present. Try to have the same results with a traditional crystallization. No way. Very difficult. This can be done continuous crystallization, which is not easy with traditional approach, but can be done, but not this kind of final result. Quite interesting. In conclusion, we can today consider desalination not only for producing fresh water for agriculture or for the people, but we can consider this technology to extract the minerals of not only minerals, but minerals of very high quality from the sea, from lakes, from river, etc. And we can go this kind of operation as a continuous crystallization process with very high value for the feeds, and more and more we will need also better membranes with better material, with no creating wetting. Eventually, forget about the permeability, was important selectivity. So we are looking to new form of a new kind of material, more selective, so you can have a mixture of 10, 15, 20 different minerals in the feed, and the membrane material giving some influence on the selectivity of them. This can be done. Different technologies are available today that have been studied in the past, not too much today, but we are starting to looking again. Imprinting polymeric material is a typical example that can help in this selective crystallization, fractional crystallization, etc. Keep in mind that also the catalytic properties of this material can be quite interesting. So to conclude, people look into desalination and learn about desalination have, in my opinion, in the hands a very interesting new industrial potentiality, not just producing fresh water that you have to sell for nothing. You have to just distribute for free. But this exactly same technology combined as in the strategy I was showing you, where you can operate on the concentrate of your RO and NF steps with MD and membrane-assisted crystallizer, you can introduce a system for producing water but producing minerals, so avoiding completely brine disposal problem, vice versa, emphasizing the value of your operation through the extraction of minerals from the brine. And that can be quite interesting, bright future for desalination. Thank you for your attention.
Yeah, okay. Thank you, Professor Enrico, for very interesting talk. And I'm sure this will also lead to